You asked the critical question about the stability of the carbon that was deposited via photosynthesis. And it was an interesting answer, and I certainly thought it was thoughtful and yet incomplete, because the answer is not simply biochar. Although I've made biochar at my farm in Costa Rica, and I use it and I applaud it, and I think it should be incorporated more and more. But Richard Teague at the farm and at the grasslands in Texas, where 11 tons of CO2 or 3 tons of carbon were deposited per hectare per year, was biochar used? No. And if you go all over the world, in China, when the FAO has just announced a carbon trading standard of 3 tons of carbon per hectare per year for grassland management, it was not because biochar was being incorporated into those grasslands. This happens by the action of nature. It happens by photosynthesis. And so, Betsy, the question needs to be an answer beyond the stability and durability and the immutability of elemental carbon. It has to be, what is the stability of the carbon deposited through the liquid carbon pathway? So I asked the professors at lunch to answer that question for me. And their answer was, surely at the very surface levels, the above ground biomass is highly labile, highly active, and the biomass in the very top layers of the soil, highly active, highly labile. It's going to be turned over very quickly. But as I invite people to see this, this needs to be in a magazine. As you go deeper into the soil via the humification process, the carbon that is incorporated into microaggregates, helped to be glued together by the glomalin that you just heard discussed, that carbon goes from being fast food at the very surface layers to slower and slower and slower food. And just beneath the surface, as it is being humified, Professor Teague and Dr. Applebaum said it's going to last in years 200 to 300,000 years. Betsy. And as you go deeper and it further mineralizes, it's going to be in the amounts of up to 500 tons per hectare per year, and it's going to last for 3 to 5 million years. Okay, so I think that that's important to have that information out in the public. I confess it's not part of my talk, but I didn't hear an answer that fully satisfied me, and that answer, in fact, does satisfy me. Okay, I've said it. Now, because I'm in that mood now, I'm feeling my postprandial aggression, I guess. I had a lunch a few months ago with one of the principal advocates or apologists for industrial, extractive, monoculture, GMO, glyphosate-enabled agriculture. And this guy is really, I'm not going to mention his name because he's actually a good friend, and there's no accounting for my judgment, but he's a great scientist. He's one of the most respected biologists of our times, and I'm having a meal with him, and I said to my friend, it's my intuition based on what I know at my organic farm in Costa Rica that we will be able to more effectively feed the world and more aggressively sequester carbon through the biologically honed over the eons practices of photosynthesis through polyculture, through organic agriculture, through regenerative agriculture, than through the glyphosate-enabled monocultures. And his answer was an important answer. His answer was, well, that's verifiable. In other words, he's saying to me, prove it. I mean, if you believe that you can sequester more carbon and grow more food using regenerative organic agriculture, then prove it. Now, it's funny how that same standard is not applied to the oft-repeated lie that you must have monocultures of GMOs and glyphosate-enabled agriculture to feed the world, that we need that because that's truly the climate-smart agriculture. That same standard doesn't apply to his position, but he sought to put me to the test, and I answered, well, in fact, I'm going to. In fact, the Carbon Underground is supporting research in Costa Rica that will verify or not my heartfelt belief. This is where my journey started at Rodale's farming system trial in the Lehigh Valley 7 years ago. The then director of the Rodale Institute, Dr. Tim LaSalle, planted the important seed in me. He brought me to the farming system trial, and whoa, and I don't know where the pointer is, somewhere. Pardon? It's okay. The big tall corn behind me is what? Right, and the stunted corn is, and it's the same corn, it's the same starting soil, it's the same water, the same farmers. But interestingly, in this year in the Lehigh Valley, there was a serious drought. And therefore, over the last 30 plus years at the Rodale Institute, you've seen the trials showing that in the production of food, now we're talking now agricultural products and not livestock, because people still want to eat agricultural products from the farm and not just livestock. And there are 1.5 billion hectares of farmland on this globe, and it's important to prove the concept of sequestration in the farming context as well as in the ranching context. And Rodale has demonstrated over time that there is equivalent yield and substantially greater carbon sequestration in the organic system than in the conventional system, except during drought years. And during drought years, the yields are between 30 to 50% greater for the organic system. So I loved that. It inspired me. And I had that in my mind that someday I would take that concept and put it to the test in the neotropics where I have my farm, because 40% of the world's population and more than half of the young children of the world live in the tropics, and we have to demonstrate that regenerative agriculture will actually feed them. So we have a farming system trial. And the farming system trial was created not on my farm because I'm certified organic and certified biodynamic, so we couldn't actually have the trial on my farm because we can't have ecocides and chemical synthetic fertilizers on my farm. So we got some pasture land that had been overgrazed for 65 years with an extraordinarily compacted soil and a dense mat of weeds, and we created 6 different farming system concepts. We have conventional, that is no-till and conventional tilled. We have organic to the NOP standards of organic, that is no-till and with permanent cover crop. And then we have Demeter standard biodynamic, that is no-till, and then the final system is biodynamic with their permanent cover crop. And then we have 3 replicants of each. We randomized the lots for soil type and proximity to the riparian areas, and we started, and the first rotation was for cassava. And unfortunately, that wasn't what I wanted. Unfortunately, while we planted in what was the dry season, we had the worst drought in anyone's memory on the Caribbean slope of Costa Rica. There's usually, even in the dry season in the rainforest, there's usually rain every couple of days, if not every day, a little bit. We had 2 months of no rain. So we had the same starter stock, the cassava, the yucca that was being planted, the same soil, randomized, the same farmers, the exact same water. And I went to the farm about 3 weeks after the planting, and this was the organic lot. I took my camera, no photoshopping, took my camera. This is an organic system. And then I turned around, and this was the conventional system. I did not doctor this. Organic, conventional. So why? I mean, it couldn't possibly be that we have magically sequestered huge quantities of carbon in this system after 2 or 3 weeks. It's just not possible. So I told the soil microbiologist, I said, you've got to come up with an explanation why there's this complete failure to germinate for the cassava. And do you all know cassava? It's one of the principal foods of the world. It's in the top 3 most commonly consumed foods. It's tapioca. Okay, that's one form of it, but it's one of the principal starches consumed in the world. So there was this marked failure to germinate. We have the same number of plants per treatment group, but we had here, by percentages, the organic and biodynamic, somewhere between 0 to 3% failed to germinate, and we had up to 40% failure to germinate. So the university that we were working with, which is the National University of Costa Rica, said, well, this is striking. Replicate this, if you can, in an even more controlled environment. Replicate this, under cloth, with the soils, with the same applications of the same ecocides and fertilizers, and see what happens in a really controlled environment. And we found that the results were identical. And here you can see conventional nearest to me and organic furthest from me. So now we're frankly puzzled. How could this be? So we looked at the bacterial dynamics, and the blue was starter bacterial biomass, and the red is biomass just about 2 months later. And what you can see is that the conventional systems, which are the furthest systems on the graph on the horizontal, CVA and CVB, they actually started out with the best bacterial biomass, but they ended up with the worst. And the conventional and biodynamic all showed really marked improvements. 5 minutes left, I got to scoot. Then we looked at protozoan dynamics, and once again there were dramatic differences in the levels of protozoan populations between the organic and the conventional. But could there be a deeper cause? Could it be that there was something going on with soil organic content with carbon? So we took 810 soil samples down to 80 centimeters, which is where either the water table or the rock was such that roots would not go below that level. We used Steve Applebaum's Earth Partners soil carbon methodology, approved as a verified carbon standard. And we have 9 months of data. We parsed out any confounding variability from compost tea application, from compost application, And after the initial tilling, there was a decades-old wheat mat that we plowed under. There was just a huge amount of fresh, labile, unstable carbon over baseline. So we then looked at different levels of the soil. Not much going. I'm going to go through this quickly for time constraints. Let me assure you that from 0 to 10 centimeters, there's just not much difference between the organic and biodynamic and the conventional. And nor is there much difference at the 10 to 20 centimeters. And you're starting to see some difference in carbon at the 20 to 40 centimeters, but it's not that impressive. 40 to 60, it's manifesting more. But let's look at the deepest level, 60 to 80. And I'll do this really quickly. You've got conventional A and conventional B. And if you look, the red is pre-till. We tilled everything because we had to break up the weed mat. Then the blue is the inheritance. The blue is that labile carbon that we put in after the initial till. Look at the huge levels of inherited fresh carbon being put into the conventional fields. And then look at the yellow where they ended up after just a few months. And then look over in the organic and the biodynamic, and you can see, for example, in the final column, organic B, look what's happening there. Unlike in the conventional, where the inheritance was burned through, was wasted, where the system took that organic bequest and deracinated it. In the organic, we actually increased the value of that legacy. So I'm going to not focus because we don't have time. But the conventional lot A lost 12.55 of the additional 13.8 that we gave it. And the organic B, just to pick two examples, we added an additional 7 metric tons to that inheritance. In every case, the biodynamic and organic treatments maintained their carbon inheritance better than the conventional practices. And as a result, there's an aggregate look at the test lots at all the levels. And as a result, you can see that in every case, the biodynamic and organic, looking at the aggregate of all the levels of the soil that were tested, had better maintenance or growth of the organic matter of carbon versus conventional. Now, these data are not statistically significant to a 95% confidence, but they paint a picture of what is happening in a real time in a field that is being transitioned from an overgrazed 65-plus year pasture to productive farming. And capturing this information is something that we in the Carbon Underground are doing here in Costa Rica and are looking to do all over the world. Thank you very much.